Welcome back to the GCSE Maths Pro YouTube channel. Today's video is on probability trees. So we're going to start off with a more straightforward question. We've got here that the probability that Jason will win a tennis match is 0.35. Complete the probability tree. So you can see we've got it drawn here. He's either going to win or lose, and we've got that win is 0.35. So on this win branch of my tree, I'm going to write down the probability. This time it's in decimals. Sometimes it can be decimals, sometimes it can be fractions. It just depends on the context. Here they've given us decimals, so that's what I'm going to use. Now, each of these sets of branches, and what I mean by that is, for example, this here is one set, another set, and another set. Do you see where they come from the same point? Each set of branches in a probability tree always adds up to 1. The reason being because let's see, if we look at this first set here, his first match, he's only got the option in terms of this tree of winning or losing. And if you can only win or lose, the probability of winning or losing in total is 1, isn't it? It's 100% of your chances. You are either going to win or lose. That's a definite. So that means that I can work out the probability of losing just by doing 1 minus 0.35, the one that I already know. And that should give me 0.65. So that's his probability of losing. Now normally this first bit makes sense. It's then that you might look at the second match, so he's going to play again, and you go, yeah, but they haven't given me information about the second match. Okay, if they haven't clearly stated the difference between this first column, so the first match, and then the second column, which is the second match, you have to just assume it's all the same. Because they haven't given us enough information, and they obviously have to give you all the information in the exam that you will need. They haven't given us specifically a second probability. In this case, we can assume that the winning chance, the probability of winning every match, whether it's his first match, second match, third match, fourth match, whatever, we just have to assume that the probability is always 0.35, okay? Because they haven't given us anything else to go by. Therefore, obviously, the probability of losing any match is still the 0.65. Okay, so each of these 3 sets of branches should add up to 1. So that's completing the tree. Now, let's look at a part B question. So I've got it here again, I've just typed it out. Work out the probability that Jason will lose both matches. So I tend to use a highlighter here. You might want to use a coloured pen, or you might be happy to just look at it. I like to highlight the options of what satisfies the question. So in this case it says lose both matches. So with my highlighter, I'm looking at my first match. I can either win or lose. They've asked us to say lose both, so I have to follow the lose line here. Now for my second match, because I followed the lose branch in my first match, I'm now looking at just this set of branches here, not the one at the top. That would be if I went along the win branch, which I haven't. So now I'm on my second match. Again, they've said lose both matches, so I have to follow lose again. Now, sometimes you might only have one option, so you can see this yellow option, lose and lose. Sometimes you might have 3 or 2 or just multiple options. You can highlight those in different colours. In this case, we just have one option. If I follow any other branch, it won't give me lose both matches, will it? So once you've highlighted whichever options satisfy the question, now we need to work out what our calculation is going to be. So between the branches of a probability tree, you're always going to multiply. The reason being is because with probability we have 2 rules. We have the AND rule and the OR rule. AND is where you multiply, OR is where you add. Now, if I think about the wording, they've said lose both matches. I realise there's no word AND or OR in that sentence, right? But you have to kind of think about it. We're saying here that the probability that he loses the first match and at the same time, not literally at the same time, but within the same scenario, he has to also lose the second match. Both is the same thing as saying and, isn't it? Lose and lose. That's basically what we're saying. Lose and lose. It's not lose one or lose the other, is it? He has to lose both, which means and. So between your probability tree branches, so you can see how I've got this first bit here for the first match, the second branch here for the second match, it's always multiply. So for this one, because I've only got one option, this yellow option as a whole, I'm just going to multiply those probabilities together. So obviously we would do that in the calculator. Normally if it's a decimal question, it's probably going to be a calculator paper. And that gives me 0.4225. So that's my probability of losing both matches. This one was a more straightforward example because we had the same probabilities for all the wins and the same probabilities for all the loses. We also only had one option, or if you think about it like one pathway, that satisfied the question, so we just had to do this calculation once. But let's look at some more examples, and each time they're going to get a little bit more complex. So Joanna is going to play a game of Monopoly and a game of Uno. The probability that she wins Monopoly is 0.12, and the probability that she wins Uno is 0.34. Work out the probability that she wins at least one game. So this is kind of our part A, part B question all in one, isn't it? We obviously are going to have to fill out the tree. So do you see how here our first column is now Monopoly, and then the second column is Uno? So Monopoly, the win is 0.12. The lose, therefore, must be 1 minus. Because in this tree, she can only win or lose. That's 100% of the chance. You're either going to win or lose, isn't it? So that would give us 0.88 for lose. Now for this one, I'm not going to copy these probabilities to the second column because we've got two different things and they've given us two different probabilities. We have Monopoly here and Uno here. They're separate. So now I'm looking at the Uno column. The win is now 0.34. And therefore lose, I'd have to work out in the same way. That's going to have to add up to 1 as well, because that's completely separate to Monopoly, isn't it? 0.66, that's for lose. Now we've got to the point where we're like, yeah, okay, I've got two of my sets of branches, but what about the third one? Well, this is where we had to figure out, does what happens in the first column, so in this case, playing Monopoly, does it affect her chances of winning or losing Uno? From the information they've given us, there's no hint as to the fact that winning or losing Monopoly is going to change her outcome in Uno. They're completely separate games. They're not dependent on each other. They're not related. So the chances of winning Uno, even if she lost Monopoly, is still going to be the 0.34, and therefore the chances of losing is still going to be 0.66. They're not related. They do not impact or influence each other, do they? They're just two different games. So we filled out our tree. Now let's actually answer the question. It says work out the probability that she wins at least one game. There are technically two ways to do this, but I'm going to go through the long way first just to explain it, and then I'll show you the fast way afterwards. So get your highlighter again and start highlighting any of the pathways that would satisfy winning at least one game. So for example, she could win Monopoly and then lose Uno. That's at least one, isn't it? Now if I get a different colour, she could lose Monopoly and therefore win Uno. There's also one more. The wording at least implies that, yeah, she wins once, but she could also win twice because that's at least once. It means at least once, if not twice. You could win both times, couldn't she? So I could highlight here, win for Monopoly and win for Uno. Do you see how I've got three different options here? Three different pathways that would satisfy this wording. So I need to do the same calculation I did last time, but 3 times. So now what we're going to do is work them out. Let's do the green one first. So win and win. Again, as I said before, it's always multiply when you're jumping between the branches in a probability tree. So to win Monopoly, that's 0.12. Multiplied by also winning Uno is 0.34. So we'll work that out. And I would just write down all the decimals. I wouldn't round anything because we're not done yet. So 0.0408, that's the probability of her winning both games. Now moving on to the yellow, winning Monopoly, but then losing Uno would give us a probability of 0.0792. And finally, the blue option. So we could lose Monopoly, but in which case we would have to win Uno. And that comes out as 0.2992 for the blue option. So I've got 3 probabilities here that could satisfy her winning at least one game. So the overall probability of her winning at least one game, we now need to do something with these 3 probabilities. So we'll go back to the fact that I said there's an AND rule, which is multiply, and there's an OR rule, which is add. So AND is always multiply, OR is add. So when we're thinking about this, she's only going to play Monopoly and Uno once, effectively. We're talking about it in the context that she's going to play one game of Monopoly and one game of Uno. We've got 3 different possible outcomes here. But if she only plays it once, only one of these will happen. So what we're saying is she could win both, which is green, or she could win Monopoly, lose Uno, or she could lose Monopoly and win Uno. Do you see how that's or? It's one of these 3 options will happen, which means this or this or this. So when you've got multiple options, it could just be 2 or it could be 3 options. What you have to do at the end is add them all. That's when we're using OR rule. So if you have multiple options, key in the word option, isn't it? You're going to choose one of them. You're not going to end up doing all of them. It's this or this or this. We're going to add them. So I just need to add all 4 of those probabilities, which is why I said don't round them too soon. Added together, that gives me 0.4192, which you can just leave it like that unless they ask you to round it. So that is the probability of her winning at least one game. That's your final answer there. So with probability trees, you always multiply between branches. If you then end up with multiple options at the end, you add them. But the thing is with that is it's always the same process, so you just have to memorize that. Okay, so as I said, that's option 1. Option 2 is when you know, because you'll get used to some of these questions, when you can kind of recognize that the question is going to ask you to highlight a lot of options, so that we had 3 options, when actually if you look at the whole tree, there's only 4 options in total. We worked out 3 out of 4. The other thing you can do is go, okay, I know winning at least one game entails win-win, win-lose, lose-win. The only one it doesn't include is losing both, isn't it? Because there's not at least one win in that. That's the only one that's not included. So what you can do in this scenario, if you prefer, is go, do you know what? I'm just going to work out the lose-lose. That's only one calculation. So let's just do that first. So lose-lose is 0.88 times 0.66, which gives me 0.5808. Now, that's the literal opposite of what we want from the question, isn't it? It's the only other option that isn't included in our question. So the probabilities, if you were to work out the whole probability tree, should add up to 1. Every probability adds up to 1, doesn't it? As we said, there's 4 options of what could happen when she plays these 2 games. So it's going to have to be, she's going to get one of those 4 options, isn't it? One of those 4 outcomes. So they must add up to 1 as a whole when you've multiplied all of the branches. So what we can do is work out the literal opposite, if that includes fewer options to calculate. And then at the end, you do have to remember to do this though, do 1 minus that probability, which gives us, if you remember what the answer was, exactly the same and technically faster. Okay, so this was still our answer, wasn't it? 0.4192. So you've got 2 options there. To be honest, I prefer to just stick with working out all of them because I think there's less chance of me getting confused or just forgetting that I need to do 1 minus. That is a risk. You might be fine with going, you know what, I would remember to do 1 minus. That's absolutely fine, I'll do that. So you've got 2 options. Okay, so we have Tina has 8 blue and 14 green counters. She's going to pick one, replace it, and then pick another. What is the probability of both counters being the same colour? So first of all, we need to work out our probabilities, and then we can work out the question. We've been given quantities here, 8 blue and 14 green. So this is where some people are also a bit confused because originally we were given decimals. It was quite obvious that those are probabilities. These are not probabilities. These are just literally quantities. So I can't do 8 and then 14 because if you remember I said before, each of these pairs of branches have to add up to 1. Well, that clearly does not add up to 1. It's bigger than that, isn't it? And individual probabilities themselves are always less than 1, aren't they? So how do I make these into probabilities? Well, we've seen examples with decimals, but you can also use fractions, and this is a perfect example of where I would use fractions instead. Because how do I convert these into probabilities? Well, if I were to pick a blue one, there's 8 blue, we are going to use that, but out of how many counters in total do I have? Out of how many possibilities are there? 8 plus 14. That gives me 22. So the probability of picking a blue counter just initially is 8 chances out of 22. Then the same for the green counters, except now it's 14 out of 22. Now you could simplify those if you wanted, or you can leave them as they are. It's up to you. Now, the thing for the second counter though depends. Have they picked a counter and put it back before they pick again, or have they kept it? In this case, it's quite obvious. You see how it says she's going to pick one, replace it, so put it back, then pick another. So If I pick a blue one, I pick it from the pile or the bag or whatever it is, I put it back, and then I'm going to pick again. That means I still have the same chances of getting blue, don't I? I still have 8 blue counters out of 22 that are there. The green is also still the same. So in this case, the second column isn't affected, is it? It's not affected by what happens when I pick the first counter. So that's still 8 out of 22. That's still 14 out of 22. Okay, it just depends on have they replaced it, have they put it back or not. So we filled out our probability tree, and now we need to work out the question. What is the probability of both counters being the same colour? So she's going to pick 2. What are our chances of both being the same colour? So let's highlight our options. We've obviously got, we could pick blue first and then also pick blue again. That's one option. The other option is we could pick green and then also green again. We can't have any other options because that would be a mixture of 2 different colours, wouldn't it? So those are our options. Now we work out the probability. So remember, we have to multiply between the branches. So for blue, we've got 8 out of 22 times by itself, basically, another 8 out of 22, which is 64 out of 484. And then for green, we've got 14 out of 22 times another 14 out of 22, which is 196 over the same denominator. So now we've got 2 possible options. Either she's going to pick both blue or both green. Both of those can't happen at the same time, can they? It's only going to be one or the other. So I'm going to add them. The reason why I've not really simplified them or just kept them the same is because let's say if you did have a non-calculator paper, you add them, they have the same denominator already. I don't need to worry about that. So technically if it was non-calculator, just add the numerators. That gives me 260 out of 484. With probability, they're not really that bothered normally if you simplify it or not. If they haven't told you in the question to simplify it a certain way, just leave it. I know it sounds kind of counterintuitive when you have fractions you've been drilled into you that you need to simplify them always. Probability, honestly, they don't normally care. So I wouldn't bother, especially if this was non-calculator, I wouldn't bother trying to simplify it. But just check what the question says. So that's my probability, that's my final answer there. 260 out of 484, as you can see it's obviously less than 1. That's our chance of getting 2 counters that are the same. Okay, so this one's, again, a little bit harder just because you can see now we've got 3 options rather than 2. And it gets a bit crowded around here when you have got a 3-part probability tree. So we've got here that there are 5 yellow marbles, 3 purple marbles, and 8 orange marbles in a bag. Work out the probability of picking 2 different colours. Okay, so again, we're going to have to complete the tree and then we'll work out the question. So if they give you a question where they've given you quantities, sometimes it's marbles, counters, whatever it is, if they've given you quantities, we have to convert them into values, into probabilities, but obviously values that are less than 1. The way I'm going to do that in this case is I'm going to stick with fractions. So, for example, we've got 5 yellow marbles, okay, that's fine. However, out of how many in the bag? Well, if we add up 5 plus 3 plus 8, we get 16 marbles. So the probability of picking a yellow marble just out of the bag is 5 out of 16. So for purple marbles, we're going to have 3 out of 16. And for orange, we're going to have 8 out of 16, which that's technically a half. However, I wouldn't simplify it maybe just yet. Okay, now we're on to the second marble. Let's read the question again, because when you're trying to pick something, so a marble, a counter, as I said, something out of the bag, we need to know, have they picked it and put it back in the bag? Or have they picked it out of the bag and kept it? So the bag has now got a different quantity. So the question here says, work out the probability of picking 2 different colours. That's implying to me that they're going to pick one and pick another, or literally just grab 2 at the same time. Which implies to me that we're not putting the first marble back into the bag. We'll take one, keep it, take the other. Okay, we're not going to put it back in the bag. They've not specified that. So that also adds another layer of complexity, really, because the probabilities here are now all going to be different. First of all, if we follow the yellow line, so I've said I picked a yellow marble as my first one. What's the probability of me getting a yellow marble again? Well, first of all, there's no longer 5 yellow marbles in the bag because I haven't put it back, have I? So there's 4 yellow marbles left, but there's also no longer 16 marbles in the bag because that yellow one that I took first is still out. So there's actually 15 left. So do you see how that can affect my second probabilities? So you just carry on, you go, right, okay, I picked a yellow marble first. So the probability of getting a purple marble is still 3 because I haven't taken a purple one yet, but it is out of 15. And same with orange, it's still 8, but it's now out of 15. And then we carry on. So the next one is if I pick a purple marble, I will still have 5 yellow out of 15. I will now have 2 purple out of 15 because the first one was purple already. And then finally, I will still have 8 out of 15 orange. The last one, if I pick orange first, I will have still 5 out of 15 yellow ones, still 3 out of 15 purple, but now I will have 7 out of 15 orange because I already picked orange. So do you see how all of these change now? So you have to be really clear. Have they taken something out of a bag, kept it, or have they put it back? That will depend. If they did put that marble back, let's say for example, the probabilities for this second column will be all exactly the same. All these numerators are the same, all of the denominators are the same because they put it back. There's still 16 marbles, all of the marbles are still there and accounted for. Okay, so if you've got a 3-part probability tree, it does get a bit messy as you can see. So now we're going to go through and highlight the options. As we saw in the previous question, you can obviously go through and highlight all the options for getting 2 different colours. But if we did that, for example, so let's say yellow and then purple, but it could also be yellow and orange, but then it could also be purple and yellow and purple and orange, and then orange and yellow. I'll have to use yellow again. Orange and purple. There's actually a lot of options. That's 6 options, which you could work out. That's absolutely fine. You could work that out and add them all up. But I feel like in this case, it's quite a lot, isn't it? Especially if we have a look at what's left, what has not been highlighted. Do you see how picking 2 different colours would leave us with, we can't pick yellow and yellow, we can't pick purple and purple, we can't pick orange and orange. So I'm actually going to go with those 3, because 3 is obviously easier than doing 6 calculations. So let's highlight those instead. The opposite of picking 2 different colours is picking 2 of the same, which means we could go with yellow and yellow, we could go with purple, and we could go with orange and orange. That's a bit easier, isn't it? And then when we add those up, we'll subtract that from 1. Okay, so yellow and yellow is 5/16 times 4/15, which if I leave as a fraction, 20 over 240. So that's yellow. Then we've got purple, which is 3/16 times 2/15, which is 6 over the same denominator. You see how we're still doing 16 times 15, 240. Purple. And then orange is 8/16 times 7/15, which is 56, and then still the same denominator. That's why I didn't simplify the 8/16 or the other ones that could be simplified, because now I'm going to have all the same denominators. So that's orange. Okay, so now we're going to add them because it's either this, this, or this, isn't it? When you add them and you've not got a calculator, they have to have the same denominator. If they already have the same denominator as we have here, you just need to add the numerators, so that's a bit easier. That gives me 82 out of 240. The only thing here is if we are going to use the opposite method of choosing the options that do not satisfy the question, we have to remember at the end that we need to do 1 minus that probability. Because the probability of getting 2 different colours is everything other than what we've just calculated, isn't it? So 1 minus, because obviously all probabilities add up to 1. Let's say if you did have this as a non-calculator, convert 1 into 240 over 240, because if you divide that, that is just 1, isn't it? And then you can subtract the numerators. So that should give me 158 over 240 again. That does technically simplify. And that's our final answer, our final probability. Again, in this case, I would leave it as a fraction. There's no point converting it to a decimal or a percentage. Just leave it in whatever format you did your tree in. Okay, so that's a little bit faster. I mean, still a lot of work though. Okay, so the last 2 questions are a little bit quicker, and I've actually seen this style mostly in AQA, possibly multiple choice or just a 1-mark question. They haven't drawn anything. They haven't alluded to there being probability trees related, but it's clearly a probability question in general. So, for a biased dice, P5 is 2/3. First of all, what is that even saying? P represents the word probability, right? So for a biased dice, the probability of getting, and then in the brackets is what you're getting. In the case of a dice, this is effectively saying the probability of landing on 5 is 2/3. Work out the probability that the dice will land on 5 when rolled 3 times. So each time it's landing on 5. How would you work that out? It doesn't seem to relate to probability trees at all. They've not mentioned it, as I said. But I, at least mentally, go, this could be probability trees. Or at least I can use that format of a tree to figure out how to calculate it. You can always draw a tree if you want, or just visualize it in your head. The way that I know to use probability trees in questions where they haven't already drawn it for you, or they haven't said draw one, right, is when there's multiple events. And when I say event, could be anything. In this case, the event is rolling the dice. There's 3 of them. There's 3. I'm going to roll it once, check the number. I'm going to then roll it again, check the number, roll it again. Or it could be, different games. It could be picking counters, whatever it is. Something's happening multiple times, or there are different things happening kind of one after the other. That's when I know I could use a tree to at least logically figure it out if you're not sure how to answer this anyway. So I'm just saying I would quickly sketch and I go, right, probability of getting a 5. I don't really care what's on the rest of it. I'm not going to write down, a branch for 1, 2, 3, 4, and 6. Or you could write not 5 if you wanted, but I don't really need to draw that. I'm just focused on the 5. So this is the first roll. That's column 1. There's a chance of getting 2/3, isn't there? Every time I roll it, there's a chance of 2/3. Then the second roll, getting 5 again, because they've said I want to get 5 every time. 2/3. And then you can always have 3 columns, or as many as you need really, but you can have 3 columns. Third roll is getting another 5, is another 2/3. And then that helps me to visualize, now I remember that with probability trees, every time between the branches I multiply. So this is just for one option, isn't it? 5, 5, and 5. That's our one option that we want to get. I'm going to do 2/3 times 2/3 times 2/3. Or, in other words, 2/3 cubed, whichever way you want to think about it, which is 8/27. And that's my answer. So you don't have to do it this way. If you read that and you knew exactly what to do already, obviously just do it straight. But if you read this and go, I'm not really sure, I don't know what this relates to, because there are 3 events of rolling a dice, it does relate to having a probability tree. And you can either sketch it and therefore figure out what to do, or you can just try and envision it in your head and go, yeah, that means I need to multiply. So effectively it's saying I need to get a 5 and another 5 and another 5, which is therefore multiply. Okay, so just a question to see where you can use the logical probability trees if it's easier to link it to certain ones that don't necessarily mention it. Okay, so our final one now is very similar to that last one. The probability that a biased dice lands on 2 when rolled twice is 0.09. Work out the probability that the dice lands on 2 when rolled once. So this one we kind of need to work backwards a bit, but again you might be like, well, I don't really know where I'm going with this. You can use probability trees, at least in logic, to help you. Again, we've got 2 events in this case. The dice has been rolled once, it was then rolled again. There's 2 events. So for my tree, we've got the first roll landing on a 2. We don't know what that is, that's fine, just leave that there. The second roll, we also want it to land on a 2, don't we? Second roll. And you can use that to work out, well, how would I have calculated it? Let's maybe put x as our probability, right? X and x, because it's something we don't know. We would have done, to work out the probability of rolling 2 twice, x times x, wouldn't we? Which is the same as x squared, which is the same thing then as this 0.09. So we know that we've taken a number, we've multiplied it not by 2, but we've multiplied it by itself. That's the key thing. And we've got 0.09. So I'm not going to half this, I'm not going to divide it by 2, because it wasn't probability times by 2, was it? It was probability multiplied by itself. So to reverse that, I go, well, if x squared is 0.09, what is just x? And you can obviously just square root this in your calculator. So square root both sides of that equation, we get 0.3. So that's the probability of landing on a 2, just generally, just once. Or each time it's 0.3, isn't it? So the reason why I used the probability tree here was just to help me figure out how to work backwards. What was the calculation that they initially did? Oh yeah, they would have taken the same probability and multiplied it by itself, and then I can reverse that. So it's up to you, but that's an option. You can always bring in probability trees if you think that the context could be related when you've got these multiple event situations. Okay, so that covers a wide range of probability tree questions. If you found this video helpful, make sure to like and subscribe, and leave down below any questions or comments that you have.